Welcome you all in this lecture on subspaces of metric spaces. So, in the previous talk, we have seen that the definition of the subspace, so I am repeating, is set if xd is a metric space and yd prime is another metric space, and if y is a subset of x and d prime is the restriction of d, then yd is called a subspace of the metric space xd. Or in other words, if you have the metric d on a set x and the restriction of d, that is denoted by d prime, on y is called, it would be a metric on y, and y with this metric is called a subspace of metric space xd. Now, I have already mentioned several examples in the previous talk, so I am not going to cover all these things. Now, the question is that what would be the shape of an open ball in a subspace? So, here is the important thing is this lemma. This lemma says that let y dy be a subspace of the metric space xd. Okay, and if a is any point in y and r is greater than 0, then the open ball with center at a, radius r, with respect to this metric dy, or the open ball with center at a, radius r, in the subspace y is equal to y intersection open ball with center at x and radius r with respect to the metric d on x. So that is the way we can find we can see the open ball in y. Let us see here is the meaning of this one. Suppose you have a metric space. Okay, this is your metric space. Let me write, this is your x. Suppose this is your y. Okay, now here you have the restriction, of course, d is a metric from x cross x to r, and d prime is the restriction of this on y, okay, which is defined as d prime xy is equal to dxy for all xy in y. Okay, so that is the way. Now suppose you have a point A. Suppose this is the point A. Let me call this is point your A. Okay, now let us define, because we have a metric D here is, you have a metric. So with respect to this metric, we can define we can construct an open ball with center A and radius R. So let us take, suppose this is your open ball. Okay, this is your open ball as RA. So open ball with center at X, center at A and radius R. Then the open ball in Y. So this is what? This is equal to, so this is the open ball with respect to the metric D. Now, what would be the open ball with center at A and radius R? So, this is your radius R with respect to the D prime. So, D prime, it would be equal to this, only this portion. So, you go from here, this one. So, this one, it means that you can take, and this we are denoting by S dash RA, which is equal to, you take the SRA and intersection Y. So this is the open ball. So now you can prove it very easily. So this we can prove. How we can prove it? You can take SRA intersection Y. Okay, so SRA what? SRA is the open ball which is defined as x is in A such that dxa is less than R. So this is the set of all points x which are less than R distance from A, and intersection Y, so I can take intersection Y. So now, because Y is a subset of X, because Y is a subspace, so it must be a subset of X. So Y is a subset of X, and therefore this must be equal to set of all points X in Y such that dyx A is less than R. But this is what? This is by definition. This is by definition, because here is this is equal to, because we are taking all the point x in X, so this is equal to, basically this term is equal to your dyx A is less than R. So this term is same as this one. It means what? It means that this is equal to the open ball the open ball with radius, the open ball at A with radius R with respect to the metric dy. So this way we can calculate the open ball. Now the question is that what will happen? Now you see it very easily. You can see that if the ball, if you have a radius is smaller than if you have a ball, suppose you have this is your, again, your set X. Suppose here you have this is my Y. Now suppose I have, this is my A, and now this is the open ball. Okay, so if the radius, okay, it is if this ball is inside the ball Y, then it is always same as R dash A, and which is, this is same as R A, because with respect to X it would be same, and with respect to a metric on Y it would be the same. So if the ball is like this, then it is. Otherwise, if suppose you have a point A and you have a ball, this one, okay, then this is the ball as RA, the ball with respect to D, and this is portion, this portion is the ball with respect to dy. Okay, so this way we can calculate, or we can draw the ball with respect to the in the metric, in the subspace y dy. Okay, now this is the main key basically in all in this subsection. For example, let us take here is now we can go little further with the help of this lemma, that is to say how we can define the open set and closed set in Y. Because I am emphasizing, keep in mind, it is very important that the open ball in Y, open ball in X, both are different. Sometimes they are same. They are same only if the ball is contained entirely in Y. Then they are same. Otherwise, they are not same. Okay, so sometimes they are same, sometimes not. But how we can calculate, how we can find the open ball in the subspace or closed ball in the subspace? So for that we have this result which says that y dy is a subspace of a metric space xd. Okay, and A is a subset of Y. Okay, then A, keep in mind, A is a subset of Y. So it is so again I am taking here is suppose this is my X, okay, metric space. Here you have this is your Y, and you have a set, this is set A. Okay, subset of A. Then this set A, this set A is open in Y if and only if there exists an open set G in X such that A is equal to G intersection Y. Okay, so if and only if there exists an open set G. Okay, so for example, you have an open set G, so you can take suppose open set you have you take any open set G intersection Y. So for example, here is you have this is your open set. Okay, this is your open set G. Okay, but this is your open set in X, and if you take the intersection with Y, you will get A. Then this set A is open in Y. Okay, so this is the main thing to here is. So we have this one, and same as the A is closed in Y if and only if there exists a closed set F in X such that A can be written as F intersection Y. Now, to prove these two statements, we will have to use the previous lemma. So let us prove the first one. So to prove that A is open, okay, to A is open, so to prove that A is open, A is open in Y. It means that every point of A is the center of some open sphere. Some open sphere means open sphere with respect to dy, okay, contained in it. So let us take SRX and SR prime X. B, this is the open ball we are denoting with respect to the metric D, and this is the open ball with respect to the metric dy. Okay, and suppose that the A can be written as G intersection Y, where G is open set in X. Then we want to prove that XA is open in Y. It means that, so we have to prove that, so X we are assuming is an arbitrary element, then we have to prove that it is the center of some open sphere with respect to dy contained in A. Okay, then we have to show that X is an interior point of A, that is equal to X is the interior of with respect to the metric dy. Okay, now since A is the G intersection Y and X is in A, and therefore X is in G and X is in Y. So X is in G, but G is open in X. So every point of G is the center of some open sphere contained in it, and therefore X is the center of some open sphere X, okay, such that this open sphere contained in G. That is to say, there exists R greater than 0 such that SRX contained in this one. Now, by the previous lemma, SR dash X is equal to what? It is equal to SRX intersection Y. Okay, but this, the open ball with center at X radius R, it is a subset of G. So this is the subset of G intersection Y. But G intersection Y is what? It is equal to A. So it means that X, so we have taken X was arbitrary. So X was arbitrary, and we have proved that this is the center of some open sphere contained in A. Okay, some open sphere with respect to dy. Therefore, X is an interior point of A as a subset of the subspace Y dy, and hence X belongs to the interior of A with respect to the metric dy, and therefore A is open in Y. Okay, now we can prove the converse part. To prove the converse part, let us take assume that A is open in Y. So assume that A is open in Y. Okay, and then we will have to prove that there exists an open set G such that A is equal to G intersection Y. So how we can do that? Let us take X be any arbitrary element. Okay, then because A is open and X is in A, so X must be the center of some open sphere with respect to dy contained in it. So there exists an open sphere SRX dash X, some open sphere, okay, with the open sphere with respect to dy contained in A. Okay, now because at each X you will get an open sphere contained in A, and therefore the A is equal to the union of such open spheres, okay, at each point X in A. But now this is what? This is by definition in the previous lemma, this is equal to the SRX intersection Y, as in the previous lemma. So we can write in this way. And now Y is independent of the union. So you can take Y outside and you can take the union over this one. So union of SRX, X is in A, intersection Y. But this is what? This is an SRX, this is your open set in Y. This is your open set in Y, and we have proved that arbitrary union of open set is open, and therefore this collection is an open set. Let us call this collection, this union is equal to G. So G is open set. G is your open set in X, because this is your SRX. So this is your open set in X. So this is your open set in X intersection Y. So where G is equal to open, and G being an arbitrary union of open sphere in X is an open set in X. And hence A is equal to G intersection Y, where G is open in X. So this way we can prove that a set A is open in Y if and only if there exists an open set G in X such that A is equal to G intersection Y. Now let us prove the second part. So second part is very simple, because we have already proved that the complement of open set is closed. Okay, so we have proved that the set A is closed if and only if its complement is open, or a set is open if and only if its complement is closed. So we have to prove that A is closed. It is same as to say that A is closed in Y. Okay, A is closed in Y. So it is same as or equivalent to say that the complement of A in Y, the complement of A in Y is open in Y. The complement of A in Y is open in Y, which is same as to say that the complement of A in Y is equal to G intersection Y. Okay, by part 1, because this is your open set. So every open set in Y can be written as the intersection of open set and the subspace Y, where G is open in X. So this can be written in this way as G, where G is open in X. Now this is equivalent to say that this is equivalent to the A is equal to the complement of G intersection Y in Y. And then this is equivalent to say that A is equal to X intersection Y, okay, minus G intersection Y. That is to say the complement of G intersection Y in X intersection Y, which is same as to say that the A is equal to the complement of G intersection Y. And now this is what? This is G is open in X. So this the complement of G in X is a closed set. So F, let us call this is your F intersection Y, where F is closed in X. So A is equal to F intersection Y, where F is a closed set in X. So this way we can get the closed set or open set in Y, okay, with the help of the open set in X, in the whole space. Now, as a corollary, we have the following result. We have result. So let Y dy be a subspace of a metric space XD and A be a subset of X. Then, if A is open in Y, and Y is open in X, then A is open in X. Okay, so it is very simple that if A, keep in mind, if A is open in Y and Y is open in X, then A is open in X. But you keep in mind, then Y as a whole space is open in itself, not open in X. For example, you see that we can consider, as we have seen that, for example, 0, 1. Okay? So this is a subset of R. But this is not an open set in R. But if we consider this as a whole space, then it is as a whole space. Every whole space is open as well as closed. But as a whole space, it is open as well as closed. But as a subset of R, it is not open. So, for example, if we take 0, 1, okay, if we take Y is equal to 0, 1, which is open in R, this is okay, and you take any open subset of this. For example, you take a open subset, say for example, you take 1 over 4 and 1 over 2, okay, which is a subset of Y. And this set is open in Y, Y is open in X, and therefore this is also open in R. So this way we can write this one. And similarly, you can prove that if A is closed in Y and Y is closed in X, then A is closed in X. So this way we can get this result. So this is very simple, very important thing. Now let's do so this is all about the closed set and the open set. Now let us see what about the interior limit point. So limit point, for the limit point, let's take Y dy be a subspace of a metric space XD and A be a subset of Y. Then X is a X in X, X in Y is a limit point of A. Okay, this is a limit point of A in Y if and only if X is a limit point of A in X. So very good. Okay, so for example, here you have suppose you have, this is your set, this is your set X, this is your Y, okay, and now suppose you have a point, this is your point X, okay. So this point X, so this is your X, and now here is, this is your A, okay, and the point X, this point X, so this is your point X. So let us take, here is you have a point X. So this point X, so this point X, or I write like this point X is a limit point of A in Y if and only if it is a limit point of A in X. So there is nothing. Okay. Similarly, the closure of A in Y, okay, is equal to the closure of A in X intersection Y. So this is so here is for the limit point, it is same, but for the closure and interior it is different. So here is X is the limit point of A in Y if and only if X is the limit point of A in X. And the closure of A, we are denoting the closure of A in Y is equal to the closure of A in X intersection Y, where this is the closure of A in X and this is the closure of A in Y. In other words, you can say the closure of A in Y is equal to closure of A intersection Y. Okay, same as in case of the open set and closed set. Now let's prove the first one. So first one is very good. So if it is a limit point with respect to Y, then it is limit point with respect to X. So let X be a limit point of A in Y. Okay. Then for every open set, then for every open sphere, this is your every open sphere in Y, we have this thing. Okay. The intersection open sphere minus X intersection A is non-empty. Now for any given R is equal to 0, we have, so we can take, this is the open ball at X radius R in capital X in the metric space X intersection A. And now then this is equal to, by the previous lemma, this is equal to, you see that here is we can take A is a subset of Y. Okay, so A is a subset of Y, so we can take this intersection Y minus X intersection A. So this we can write as intersection Y because A is a subset of Y. So it is always subset of Y. But this is equal to Y. This is equal to this thing, which is the open ball with center at X and radius R with respect to dy minus X intersection X. So this is non-empty. So it means that we have seen that X is a limit point of A in Y, and we have proved that this is non-empty. It means that X is the limit point of A with respect in capital X. So the one part is and the converse can be established by retracting the above steps. Now to prove the second part, let us take, since the closure of A in X, the closure of A in X is closed in X. Okay, closure of A in X is closed in X. Then we have proved that then by theorem this set intersection Y, the closure of A in X intersection Y is closed in Y. So this is closed in Y. Now this set contains A, and since this is the intersection of all closed subsets of A containing A, we have the closure of A in Y is a subset of closure of A in X intersection Y. And on the other hand, this closure of A in Y is closed in Y. And then the closure of A is equal to F intersection Y, where F is closed in X. And since A is a subset of closure of A in Y, F is closed in X containing A. And since the closure of A in X is the intersection of all closed sets containing A, we have the closure of A in X must be a subset of F. And hence, the closure of A in X intersection Y is a subset of F intersection Y. But F intersection Y is what? F intersection Y is equal to the closure of A in Y. So it is equal to closure of A in Y. So this way we can prove that for the limit point x is a limit point x is a limit point of A in y if and only if x is a limit point of A in x. And the second thing is that the closure of A in y, okay, closure of A in y is equal to the closure of A in x intersection y. So this way we can write, here is this one. So now we can continue our previous talk that we have the exercise which says that y dy be a subspace of a metric space xd, and prove that a subset M of y is a neighborhood of a point y, okay, if and only if there is a neighborhood n of y in x such that M is equal to n intersection y. So by using the similar argument as above, we can prove this result, and whose proof is already given here. So I stop over here. Okay, thank you, and we will continue in the next talk about the complete metric space.